So far we've talked about one variable data. We're really just looking at one variable. In bivariate data, we're looking at two variables. And most of the time, being creative mathematicians, we call them X and Y. So bivariate just means we have two variables. We're comparing two variables. Now it can be, oh my gosh, I can't believe I had a typo, summarized the following ways. We can have scatter plots where we look at the graph to look at the relationship. What's called the correlation coefficient, which is a summary statistic that measures the closeness of the relationship. What is called the least squares regression line, which is an equation that can be used to predict one variable given the other. So let's talk about correlation. What does that mean? So when we have a scatter plot, that's a graph that shows a relationship between two quantitative variables. So when we're talking about these, we're talking about quantitative values. You can't really do this with qualitative. I can't make a scatter plot with color and type of clothing or something like that. It has to be quantitative. Now each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is on the horizontal. So what would that be? If it's on the horizontal, that's going to be our X. Explanatory is the X. The response is going to be on the vertical, so the response is the Y. So the response variable is the variable whose value can be explained by the X. So thinking about back in Algebra 1, you have your independent and dependent. So the response depends on the other variable. Your response depends on the explanatory. The two variables display an association if knowing the value of one variable is useful in predicting the other one. Now there's three things that are three aspects that we talk about when we talk about association of quantitative variables: direction, strength, and form. So the direction refers to whether greater values of one variable tend to occur with greater values of the other, or with smaller values of the other. So we're looking at either a positive association or a negative. So positive would mean that it's going up, and negative would mean that the graph is going down. Now, strength of the association is how closely it follows the relationship. So how close the pattern fits, the tightness of the pattern. Now, the form of the association, it can either be linear or it can be a more complicated pattern. You could also have patterns that fit a quadratic or other type of a function. But the main ones we're going to look for are linear. Now, two variables that are linear related are said to be positively associated if whenever the value of one variable increases, the other one increases as well. They're negatively associated if one increases, the other one decreases. Oops, trying to turn the page here. So let's look at some patterns. Now, two variables have a linear relationship if it resembles a straight line. So we've got some patterns here. Explanatory, again, is the X. Response is the Y. So we can look at these different patterns. This is definitely linear. It's making that nice linear pattern. And notice that it's going up. So this would be considered a positive linear. I guess I could have wrote out positive. This also follows a linear pattern, but it's going down, so this would be considered a negative linear. The next two aren't forming a line, so these two would be considered non-linear because they make more of a curve. Now the last one, this is considered no relation because they don't really form a pattern. So you want to look for those key things when you're looking at a scatter plot. So our first example, we have a golf pro wanted to investigate the relation between the club head speed of a golf club, measured in miles per hour, and the distance that the ball will travel. He realized that there are other variables besides the club head speed that determine the distance the ball will travel, like the club type, the ball type, the golfer, and the weather conditions. So to eliminate all of these other variables, the pro used a single model of the club and ball. One golfer was chosen, 70-degree day with no wind. So they try to cut out any other variables that could change the outcome. And they plotted these, here are the data. So these would be our X, and this would be our Y. So, because he's trying to see if the club head speed affects the distance. So this would be our explanatory, and this would be the response. And so here's the scatter plot. And it does look kind of like it's making a little bit of a line, and it looks fairly positive, is what I would say. Now we can make a scatter plot using the TI calculator. You can also do it in Excel. I've included both of those instructions so that you can do this yourself. The explanatory variable, or the X, is going to go in L1, and your response is going to go in L2. Now, once you've put your variables into your list, we're going to go to stat plot to look at the graph. Now, I'm going to go ahead and do this one. I'm going to show what I'm doing very carefully. So to put it in the list, we're going to go to stat, and the first option is edit. That's where we go to enter our lists. L1 is going to be where I put my X values, and we're going to put our Y values in L2. So stat, edit. Now to clear out a list, you up arrow to where it's highlighted the L1 and press clear, enter. And then I'm going to type in the values from my table. 100, 102, 103, 101, 105, 100, 99, 105. And making sure that they match up. And they do match up. Now I'm wanting to make a statistical plot, and that's called a stat plot here, and it's in blue over the Y equals. So I'm going to be pressing second Y equals, and those instructions again are on the next page. And notice that it says plot 1 is off. We're going to press enter here, and then I'm going to press enter on the on. Now there's different types of graphs we can graph here. Right now the first option is a scatter plot. That's what we're wanting. Notice that it also has histograms and box plots. Those would be for one variable, but we're doing two, so we're fine with everything else. Now I wanted to see if I actually included, I did. So we've got the scatter diagram icon is selected. X list is L1, Y list is L2. And to make sure that we fit everything in, we're going to press zoom and then go to number 9, which is zoom stat. So I'm going to press zoom, and you can either arrow down or you can just press the number 9 and it goes to zoom stat. And it gives me the same picture. Now this one was created using Excel, so it doesn't have the dots, but this is the same picture that we were given in the previous diagram. And it does look fairly linear. So I would say this is a positive linear relationship. So we can talk about that it's positive or negative. We can talk about that it looks linear, but how strong is it? So let's talk about how we measure the strength. Well, to figure out the strength and also the direction, we can look at what is called the correlation coefficient. Now, looking at these diagrams, we really want a numerical value to discuss the strength, because looking at these, that's hard to really talk about how strong they are. So let's look, and I wish I had put this on the same page. Which ones look positive and which ones look negative, and then which ones look the strongest and which ones look the weakest. So I'm looking for the positive one that's the strongest. Maybe I should put this up here. Let me redo the chart here. So none, positive, and then negative. So which one looks to be the positive, strongest relationship? Well, I really think that's B right here. That's really, really, really strong, right? So I'm going to put it on this end of the spectrum. Which would be the next strongest as far as a positive relationship? Well, I'd probably go for this one. It's still positive. I can see the relationship, but it's not quite as strong as that one, so I would put that one maybe next in line. Now, are there any more that look like they might be positive? Well, I would say E is going up, and so is I. But which one looks stronger as far as them being closer together? Well, I think I looks stronger than E. So I would put I here, whoops, and E here. Now, is there any picture that looks like it? I can't tell whether it's positive or negative at all. That would be C. I would say C would be no relationship at all. So now I'm down to the negatives. So here's a negative. Here's another negative. Let's see. This is another negative. And we have another negative here. Okay, so we got 4 negatives. Which one is the strongest out of those negatives? Well, I'd say D is very strong. Maybe not as strong as B is positive, but it's a pretty strong negative. And then I might go with G next. And then H compared to A. Which one would be your next in line? I would think as far as patterns, I might put A above H. Now, notice that we put those kind of on a spectrum from strongest negative to strongest positive. This is kind of how we do a correlation coefficient. If it's no correlation, it would have a value of 0. A strong positive would be a 1, like a positive 1. A very strong negative would be a negative 1. And everything else would be kind of in between there. So if we think about 1 being a perfect positive, I might say that B, I mean, it's really strong. I might call that like a 0.97. That's pretty strong. Now F wasn't quite as strong. I might say that's like a 0.7. Then we said I would be next in line. I might call that like a 0.4 or a 0.5. It's still positive, but it's getting weaker. E is getting weak. So this one I might say is a 0.2. It's still positive-ish, but it's not really there. Now C has no pattern whatsoever. And I just put the value R. We measure this correlation and we call it R. R is what we use to represent the correlation. And I should have said that. That's so it's called R. And we could guesstimate the others using the same type of pattern. I would say D is negative, not quite as strong as B was positive, so maybe this is like a negative 0.8. And we could keep guesstimating. But there is a way to actually find it, to find that R value. So that statistical correlation, it'd be better to have a real number, right? And if we had that number, it would tell us how strong it is. It would also give us the direction. And for the population, the correlation coefficient is represented by this Greek letter rho. It looks kind of like a P, but it's actually rho. For the sample, it's R. Now this is a crazy formula. It's called the Pearson correlation coefficient formula. We don't actually have to use this formula. I'm going to show you how you can use your calculator to find it. So I'm going to go back to our example that we had before. Now we have to do a couple of things in the calculator to make your calculator give you this correlation coefficient. We're going to press mode. And we have to go down to the next page. And I see this stat diagnostics. Stat diagnostics has to be on. If it's off, you will not get the correlation coefficient. Now, we think this is a linear correlation, right? So what we're going to do next is we're going to press stat, and then we're going to arrow over to calc. So press stat, and we're going to go to calc. Option 4 does what is called a linear regression. This is going to give us an equation that can be used to model the data, and it's going to give us a couple of other things. So let me press this. Now it gives me, it says, is your x values in L1? Are your y values in L2? Do you want to store the equation? You can actually store it in Y1 if you wanted to. But right now we're just going to press enter. And I'm going to show what all it gives me. It says y equals ax plus b. And it says a is 3.166. So that's going to be the slope of the line. B is negative 55.797. That would be the y-intercept of the line. R squared, we're going to talk about that later. That's just r squared. But it will be an important feature as well. And then it gives me R is 0.939. This means this is actually a strong positive correlation. That's almost a 1. That's great. So I got my correlation coefficient, and it tells me how strong it is, which is awesome. So we don't have to use the whole formula, which is great. Now, we talked about that value is going to always be between -1 and 1. So here's some examples of a perfect 1. So if you can't see, I know it's hard to see, these didn't come out. This is a perfect 1. This would be a 0.9. And we would say this is strong. 0.4 would be moderate. So 0.4 and up, I would call that moderate. I would say if it's over 0.8, it's going to be strong. This is a perfect negative. Notice that everything's in line perfectly. This is a really strong negative, negative 0.9. This is a moderate negative, negative 0.4. And then no relationship would be a 0. This is also would have an R value of 0, but it does have a pattern. This one is not a no relationship. It's just nonlinear. So you always want to look at the scatter plot first. And there's more than one way to measure the correlation. Now the correlation coefficient is not resistant. So if you do have an outlier, that's why it's important to look at your scatter plot. An outlier will affect that R value. So you'd want to be very, very careful with that. Correlation measures the strength between the variables. And just because two variables have a strong correlation, it does not mean that there's a cause and effect. Now I probably should mark down that let's actually write down what means it's strong. So strong is if R is greater than around a 0.7. If we're between around a point, I'd say 0.4 and 0.7, I would consider that moderate. And then if it's less than a 0.4, I would consider that weak. So we should probably write that down. Now, like we said here, just because there's a correlation, just because there's a pattern, that does not mean that there's a cause and effect. Let me go into detail on that. Ice cream consumption has a positive correlation with drowning rates. Does that mean ice cream causes drowning? No, it just means people tend to eat ice cream a lot in the summer, and they swim a lot in the summer. The sales of lawnmowers are positively correlated with warm temperatures. Does that mean lawnmowers cause global warming? No. Greenhouse gas emissions have drastically increased globally, and meanwhile, global surface temperatures have been steadily increasing for decades. Could those actually have a cause and effect relationship? The number of hours a person spends working per day appears to be negatively correlated with the number of years a person is expected to live. Now be careful, just because there's a correlation, it does not mean there's a causation. Alright, could we match a diagram with a correlation value? So I'm going to give you a chance. Which one of these would match up with the first one? That'd be C. That's a perfect negative. Which one? Ooh. 2? What do you think 2 would be? That's better than 4, so I think that would be the D. And this would be the A, and this would be B.